Right, now hard JAL. This is how to do complicated things in JAL the easy way. It comes out of a conversation that we had about a month ago now with Davey when he was doing the how to use the analog to digital converter in JAL, and he produced this code which was set ADRES H equals set the AD con equals 3F and then read ADRES until such and such change. And there was all this quite complex stuff. And it looked like it kind of drops out of the sky, like some guru somewhere produces that. It doesn't. It's actually quite easy to do. I'm going to move him again. Whoa. There we go. If you buy a modern PIC chip, anything that's come out in the last 3 or 4 years, they come with a ton of peripherals on them. Right, the early ones, like the 675 that we use, have got half a dozen peripherals. They've got analog to digital, they've got PWM, they've got not an awful lot more than that. They've got a couple of timers. The modern ones have got lots and lots and lots of things. They have analog, they've got operational amplifiers, they've got comparators, they've got voltage references, they've got all sorts of groovy stuff. And also the peripherals can be used without the processor having to use them. You can set up a servo, and the only time you talk to that servo is when you change the position of it. You just say, oh, set that servo to 80. And then further down your code, set that servo to 90. And you don't have to keep putting the servo up, bringing the servo down, timing out the 20 milliseconds, putting the servo up, waiting for the millisecond, putting the servo. You don't have to do all that. The peripheral will do all that. You just tell it what values you want. And the other thing that the modern chips do is you can put any of your signals out on any of your pins. So if you're designing a printed circuit board, you can have all the input pins to the left-hand side of the chip and all the output pins to the right-hand side of the chip, which makes designing the board easier, which makes laying the board out easier. It means it's easier to get to a single-sided board design, which you can then CNC or print yourself in the back room rather than having to wait for them coming from China, all because of complications inside the silicon. That's the good news. The bad news is that for all that complication, wait a minute, there's an example of a modern data sheet, front page of the data sheet. Look at all the digital peripherals. It's got dozens of them. It's got I2C, SPI, RS232, RS485, numerically controlled oscillators, captures, compares, complementary waveform. It's got a ton. And then there's the analog over here, comparators and DACs and ADCs, all sorts of stuff. The bad news is that all that complication comes with complication. In order to do that, you have to set all sorts of bits and bobs inside the processor. And all these bits and bobs aren't in the one place. They're smeared across the PIC chip. If you want to set up a PWM, as we'll see in a minute, you have to adjust the PWM, you have to adjust the timer, you have to decide what pin it's going on, you have to decide what oscillator it's using, you have to decide all sorts of stuff, and they're all in different places. So the data sheet gets bigger and bigger and bigger. There are now data sheets that are 15, 16, 1700 pages long. Just for comparison's sake, the standard copy of War and Peace that you buy from Amazon is 1200 pages long. The Bible is about 1300 pages long. And you're getting data sheets that are bigger than that. And the thing is that with a data sheet, if you're one bit wrong, if you're a 1 where it should be a 0, or a 0 would be a 1, your thing doesn't work. It's not like that in the Bible. Trust me. There's all sorts of dubieties and stuff like that. And if you look at the way it works on a 675 has got 2 banks of special function registers, bank 0 and bank 1, and you change a bit, and that changes whether you're looking at those special function registers or those special function registers. Modern chips might have 32 banks or 64 banks of special function registers. So you have to pick which of the the 64 banks or registers you're going to alter before you start altering it. It really gets complicated. However, it's not all bad news. The people that work on JAL, the JAL team, I'm making him small now, have been working hard to keep up with this. As every chip comes out, Microchip put out a file called the whatever it is, the 16F 234078 or whatever the hell the new chip's number is. They bring it out, and they also bring out an include file. And the include file is a text file of all the settings, all the variables and what they all do. The JAL guys have written a Python script called pick2JAL, and pick2JAL reads that and converts it in to JAL, so that the JAL now knows how to deal with that. And it turns out that the JAL editor will let you see that stuff. And that's kind of what I'm going to do today, is take an example and walk through it. All the stuff about making complicated things happen, Microchip already provide ways of doing that. So I'm going to show you how Microchip do it, and then I'm going to show you how to convert Microchip's answer into JAL. It only takes a wee bit of work, and it means that you can do it by simply on a GUI changing things rather than going through that great big complicated data sheet and learning it. So moving on, if you're going to get JAL, that's probably where you're going to get it from. Right. As I said at the top, the list of websites and stuff are already here. This is in the package, obviously, it's in the presentation, so you don't have to scribble down the URL. It'll be in the chat at the end. That's where JAL comes from. However, there's also the JAL, that gives you JAL, the language, and it also gives you JAL edit. But there's another thing called the JAL lib, which is on GitHub. And if you just go to there, and where I've see that yellow ellipse there, if you follow the yellow ellipse all through the rest of this presentation, you'll see what I'm talking about. If I go there where it says code, I can download the latest version of JAL lib. Now, that's all the stuff in the JAL lib on the right, and that's all the standard JAL install that I just installed when I installed JAL on the left. And if I simply select everything in the right, copy and paste right over the top of the standard JAL install, it won't break anything. But what it will do is make everything be right up to date. Right? This was done on the 10th of April 2021, about a month ago, and I've got the compiler that was compiled on the 5th of April. So now everything's right up to date. Right? One of the things Brendan just mentioned was that if you right mouse in the Arduino compiler, you can comment and uncomment. There's also a thing that he hasn't noticed yet, and it's going to blow his mind, that if you go to something like that there, which represents a file, and right mouse, you can open that file and examine it. And we'll be doing that later on. And that lets you see the internal workings of the JAL that we're working on. So moving on. Similarly, if I go to MP Lab, I can download the latest version of Microchip's MP Lab. This is the compiler for all the PIC chips, and it includes all the include files for all the PIC chips, and it includes everything the MP Lab are giving out to public, and it's enormous. It's 1.1 gigabytes before it unpacks. So it unpacks to 2 or 3 gigabytes on your hard drive. So it's quite a big install. When you start installing it, you tell it you want to install the IP Lab, and then it says, do you want to go to the web page for the compilers? Do you want to go to the web page for Harmony? Do you want to go to the web page for MCC? Now we're going to install these two, but we don't have to go to the web page to install them. We simply install the XC compiler. And there you are. Agree with the install. And away we go. So once I've installed MPLab and I've installed the compiler, if I go to Tools, Plugins, I can select whatever plugins I want to install. The two that I'm going to need to use are MPLab Code Configurator and MPLab Harmony. Now, MPLab Harmony is for big ticket items like a bootloader, a TCP/IP stack for connecting to Wi-Fi, USB stack for connecting to a USB device. All of those you can get for nothing out of the Harmony configurator. But for what we're doing, the MPLab Code Configurator is plenty. So I select those two. I then click on Install, and it installs them for me. And then I click Close. In MPLab, I can simply open, go to File, press New Project, and open a new standalone project. I decide what pick it is, and I've only really got the one pick assembler, the one that I just installed. Now, while we're going on here, I'm going to say that this came from a member who wanted to do a traction controller on one of the modern picks. So that's what I'm aiming at. Once I've completed the new project, I don't add any code to the project. I don't start a new main file. I don't start a new anything. I simply say I want a new project. And once I've got a new project, I go to this MPLab Code Configurator, which is in Tools, Embedded, Code Configurator. And suddenly my screen explodes. I've got dozens of tabs open all over the place that are a bit frightening to look at. However, all it is the windows that were already open have got a couple of extra tabs each one. We're about to shut most of them. Anything that comes up, I will simply agree with, which is, where do you want to put your configuration? And I'll put it in the same thing, my PWM traction, I'll put it in there, I'll call it my config, that's fine, so I'm pressing save. Now, the first thing that I'm going to do here, if you'll go back here and look, it suggested that version of the chip, which is an SMT part. I don't have an SMT part. Mine is one that you can stand on and hurt your feet. It's the plastic dip version of it. So the first thing I do is I go down here and I pick the P-dip. And as soon as I pick the P-dip, it changes to the chip that I'm actually using. I'm also going to set this notifications tab, right? That pin manager grid view is the one that wakes up in, which is this one with all the little padlocks. See all the little coloured padlocks there? Yep, but I'm going to move across to the notifications page, because that way anything that it has to tell me about will appear in this lined area at the bottom of the page. I want a 4 megahertz system clock. Now, the reason for that is if you're running a PIC chip, it takes 4 steps of the system clock to do anything. So if I run it at 4 megahertz, then I get 1 million operations per second, which makes timing things much easier. You don't have to do that, but I do that because I'm a nerd. So in order to do that, in the easy setup here, I just set my system clock from 1 megahertz. I simply change it from divide by 4 to divide by 1. And lo and behold, I've now got a 4 megahertz. I simply change these values. I now want to have a pulse width modulation output. I want traction. So to add PWM, I simply go over here to this window and select the PWM. Double click it. And the first thing that happens is down here, I get a warning saying if you're going to use PWM, you need to configure timer 2. Now, I didn't know that. That's somewhere in the data sheet, but I didn't know that. But it's telling me that. But that's okay. So all I need to do next is go and configure timer 2. I'll go to timer and open it up and select a timer 2. Now, our PWM is to run at 4 milliseconds or 250 hertz. We had a discussion through the week on what's the best pulse width modulation frequency for a motor, for a traction motor. And it depends very much on the motor that you're trying to drive, whether it's an old Hornby or a Dublo, or it's a modern one. Bachmann's, they all have different motors that respond to different frequencies. Right, now that's a discussion for somewhere else. But at the minute, we decided that we wanted 250 hertz. So to get 250 hertz, we need to get 4 milliseconds in that box there. So to get 4 milliseconds in that box, I just have to change these two here, the pre-scaler and post-scaler. I've got no idea what numbers that changes on the chip or anything else. I simply know that if I vary those two, I'll get different settings here. So I twiddle them. If I change that from 1 to 1 to 1 to 64, then it goes from 64 microseconds to 16 milliseconds. And 4 milliseconds is right in the middle of that range. So once I've got that set to the right range, I simply type 4 milliseconds or 4,000 microseconds in there, and that'll do everything for me. Right? If I wanted other frequencies, then I can put them in there. Right? I went away and looked up the most popular frequencies for locos, and there they are. And I could put any one of those ones into that box, and it would let me set this up for whatever loco I'm about to use. So now that I'm finished with the timer, see the timer to the right? I go back to my PWM tab to get back to setting that up. Pulse width modulation signal has a value that goes from 0% to 100%. So I want the values that go from 0% and the value for 100%, which is always on. At 50%, the thing is on for as much time as it's off. So 50% of the energy gets to the motor. At 1%, it's hardly on at all. No energy gets to the motor. At 100%, it's on all the time, and all the energy gets to the motor. So I need to find out what the numbers are here. So what I do is simply plug in 1%, and it gives me a PWM DC value. I've got no idea what PWM DC is. Right? That's some setting somewhere in the bowels of the data sheet. But I know that if I set that to 2, I get 1% out from a PWM. That's interesting. Wonder what happens if I set it to 99%. Oh, if I set it to 99%, then I've got to put in a value of 248. So I've just written those down on my bit of paper. 1% is 2. 99% is 248. While I'm at it, I'll put a couple of other values in there. 25%, 50%, 90%. And I'll just take some notes on my scratch pad of the numbers that I need to do to get this pulse width modulator to work. I'm nearly finished. I want this PWM to come out pin 5 in the chip. Yep. So I could have picked any pin, but I chose port C, pin 5. See at RC5, which is pin 5 of the chip. There's pin 5 of the chip, port C, RC5, and I clicked on that little padlock, and that locked this signal to that pin. I can't have port A pin 3 because that's the master clear, and I'm not getting touching that. Now, that's not because I'm going to put a reset on there. It's simply because I need that to get programming the chip. So it's not allowing me to use that pin. The two supply pins, I'm not allowed to use. The reset pin, I'm not allowed to use, but I could put this out on any other pin. And if I was putting other inputs in, I could put them in any other pin as well. Right? Meanwhile, I still haven't written a bloody line of code. So I'm finished. At this point, I go up there and I press the generate button. And that generate button will generate the project for me. Right? Bump. And I empty I get rid of all the tabs that I'm not using. And there's the project already written, completely written, working in Microchip C. So if I'm working with a Microchip compiler and I'm quite happy using Microchip C, job's finished. I'm done. But I'm not finished. I want to do it in JAL. So I've got a wee bit of further work to do. Right? So I've got to now get this from C to JAL. Now, the main program that I just wrote has a line called include MCC, that's the microchip configuration tool, .h. If I go into the microchip configuration tool, it has got 4 other includes. That includes the device configuration, the pins, which pins connected to which peripheral, the timer 2 settings, and the pulse width modulation settings. And each of those files points to another H file, and each of those points to another C file. So I've got this chain of files, and it turns out there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different files. I've got all the code to do all this good stuff splayed right across them. Most of them have only got 1 or 2 lines in, but there's 10 of them. It's a mess. Now what I could do is go and copy the stuff from all of those files and put it in the top of my JAL file, which would give me a great big lumping file with all this garbage in it, which I would then have to go through. Or I could make 10 little JAL files and include them all, because JAL's got an include exactly the same way as C has. So I could include them all and includes and all that good stuff. But that leaves me with lots of files to track, and that's messy. So how about I include all the hardware stuff, all that nonsense that I was just generated into one JAL file. And that way I get the best of both worlds. The JAL that I'm working on is clean, and all the stuff that I've just generated is kept in the one place. So that's what I intend to do. I'll take all the auto-generated stuff, I'll put it in my JAL file, I'll convert it from C to JAL, and once I'm finished, I'll export the whole lot back out into a separate JAL file. So, in JAL, I'm going to put a single 1-line program. It's the name of the chip that I want to use. If this compiles, then JAL's already heard of my chip. JAL knows about my chip. And if JAL knows about my chip, it knows the names of all the registers, it knows what the PWM is, it knows what the timer is, it knows all that stuff. I'm home and dry. If that doesn't compile, game's a bogey, because this won't compile anyway. There's no way I can get this to compile unless JAL has heard of this chip. So the first thing I do is I put that 1 line in and I get it to compile just by pressing the compile button up here. And then I go back over here and I start opening, see all those files that we generated. And I select all, copy, back over here and paste. And just take all the stuff that I generated automatically in JAL, in C, and paste it into my big JAL file. Now, if I put the cursor at 16F18344, the name of my chip, I can right mouse, open that file And there is the file opened. So if let me just go back and do that again. That's my PWM trials, but I'm noticing that that file is there, that file title is there, and I can now click on that to see what JAL says. I've already got what C says, but I need to see what JAL says. So what I do, I know, for example, that in C, that double slash is a comment. Yeah. In JAL, it's hyphen hyphen as a comment. So in my JAL editor, I simply go to edit, replace. I search for all the double slashes and replace them with double hyphens. And there, all my comments have suddenly come good. Also, in C, I get pragma config. I get hash pragma config in C. In JAL, we write pragma target, if you've ever looked at any JAL. And so I can convert all the hash pragma configs to hash pragma targets, copy and place, replace. And then I've got all these equalsies. In C, you use pragma target such and such equals so and so. In JAL, there's no equals. So what I do is I replace the equals with nothing at all. In C, it's on. In JAL, it's enabled. In C, it's off. In JAL, it's disabled. And simply by searching and replacing, I get rid of 90% of the errors. So once I've done that, the next time I compile it, it goes to this fixed OSC. Got no idea what fixed OSC is. Right, down here it says unknown pragma target fixed OSC. I've got no idea what that is. I'm stuck. However, if I go over to JAL and ask it, I simply go click on the JAL page. Right, as I say, I've got no idea what fixed OSC is. So I go over to the JAL file and search for it. And there it is there. Fixed OSC is the external oscillator mode. So I read this and it turns out I want the external oscillator to be off. So what that should say is pragma OSC, OSC is off. Because that's the off is what I want, oscillator not enabled. So I'll change that to pragma OSC off, and that will now compile. And I go through that, finding out each of these little tricks. What's it called in JAL? Changing it, making it work. Then I get to all the bits. Now I've put, that's the actual C over to the right there. And that's the JAL that I wrote. And if you look, procedure TMR2 start timer is void TR2 start timer void. It doesn't take an awful lot of conversion there to convert that little void in C to that little procedure in JAL. And there's the stop timer one, and it converts from there to there. And there's how to read a timer, and there's read timer in JAL. And simply by converting it one little function at a time, you get all these things. Now, it turns out that for what I'm about to do for the PWM, I don't need the vast majority of these. I don't need to start the timer to timer, or stop the timer to timer, or read the timer. I ain't about to do that in my program. But I've now had all these little bits of JAL given to me for nothing. So I might as well take them and put them in my big JAL in case I need them sometime in the future, the next project. Eventually, after about half an hour of going through this and converting it, going over to JAL and back to C and back to JAL, I end up, it's all sorted out. It compiles without any errors. And I've now got a JAL program that will compile that does exactly the same as my C program. The only problem that I have is that the JAL program doesn't do anything. I haven't actually told it what to do. So I'm going to select all of that garbage, copy it and paste it into a brand new file called hardware. And now my JAL program has got a single line that says include hardware, and that includes all the garbage. Now I can start writing the JAL to do whatever it is that I want to do. These were some of the program things that I found. They now live in hardware.jal. PWM initialize. Load the duty value. Load the duty value. That's the only ones I'm using. And that's loading it with a value. And the values there are, remember I looked up, 2 gives me 1% and 248 gives me 99%. And if I just bung those values in, that'll make the PWM work. And that there looks much more like a JAL program that we would write, and much more like a JAL program that we would debug and make sense of than all that happy garbage over in C land. This is completely understandable. So at that point, that compiles. And if you look, it compiles to 4,000 lines, 5 different files, but no errors, and it actually makes a working JAL program that we can now put on a chip. And I'm not going to say that I'm going to put it on a chip without putting it on a chip. That silver box, top right, top left, is a USB connector to give me 5 volts. So the 2 wires for the 5 volts go straight to the top 2 pins of the chip. Pin 5 in the chip I take to my scope. There's the values. Remember I said I scribbled those down. For PWM DC, if I set it to 2, I get 1%. If I set it to 248, I get 99%. And there's the other values in between. So having built it, soldered it onto a board with my soldering iron, programmed it, there's what we get. My little face is in the road. It's supposed to be 250 hertz. It's 250 hertz. At 1%, I get 1%. At 10%, I get 10%. At 50%, I get 50%. At 90%, I get 90%. And at 99%, I get 99%, all at a solid 250 hertz. So, if I add a MOSFET to that circuit now, plus a driver, I can make DC traction work. If I add a relay, I can control the direction of the DC traction. Does it make your train go forward or backward? If I add one of these little I²C displays that Neil's going to talk about next week, we can put a number on it from 0 to 100. We could add a rotary encoder. Oh, by the way, the I²C for the display and the rotary encoder are just other includes back at, back at the, where the thing is with all the chips. I just say, oh, add an I²C and add a rotary encoder. I could add non-linear power profiles so that it gives me more pech at the bottom end of the throttle. And we've now got a new pocket money project, a high-tech DC throttle. And I only put that line in there to noise up Davy Dick, because now there's going to be people all over MERG emailing them and phoning them and asking them when the high-tech DC throttle's available and who's doing the printed circuit board for it. He's going to have to ask me for the code for it, but I'm not giving him it, so he can stick. Actually, discussing this with a couple of people after I did this, and somebody was suggesting it might actually be worth putting together a tool that lets you change the frequency, as well as letting you change the PWM, to make a tool for characterizing motors so that you can make your motors work to their best. What's the best frequency for this to get traction in this loco. So you could actually use it to design improved traction per loco. And you can make an actually quite useful tool out of this one wee chip with practically no hardware. And that's for discussion at some other point in the future. That wasn't what we're here to talk about today. In putting this together, I used VM Workstation, the same thing as I do every time I do the Windows nonsense on a Sunday. MP Lab, I've just put this slide up so that you can see the actual version numbers if you want to go and get a copy and try and do it yourself. There's nothing here that's hard. Obviously, Microsoft PowerPoint. I used Inkscape simply for, you know, the slide with the files and which file links to which file. I just used Inkscape to draw that, that's all. The rest's very straightforward. Charlie Cochin provided the original idea and has been discussing back and forth with me for it. Davey did the earlier presentation on analog input, and that was why we're doing this at all, to discuss how you get from a data sheet to a proper working project. And Keith put some smashing ideas in about what we do with it and where we take it. Any questions?